Hello, good morning and welcome to ESST1006, Human Impacts on the Environment. For this particular lecture, we're going to be talking about global climate change, and in particular looking at global climate change in terms of what causes it, what are the drivers behind it, what are the pressures caused by those drivers, what are the current states and trends in the atmosphere and the hydrosphere, which are the most responsive part of the Earth to global climate change, and how those states and trends feed through to impacts on humans through changes in ecosystem services and functions. And finally, what are some of those responses? Okay, so global climate change, or in this lecture we're going to go through global climate change. What is it? What is global climate change? You've probably heard all about it and maybe even studied it in some of your high school courses. But here we're going to just take a look at some of the state of knowledge, just briefly, on what global climate change is. We'll take a look at the causes of global climate change, drivers, which is basically an increase in human emissions into the atmosphere causing global climate change. So global climate change is really a result of air pollution by human societies. We'll take a look at some of the pressures, as I said, caused by these increases in human emissions, what it means for the atmosphere and also for the hydrosphere. We'll take a look at the state of the atmosphere and how it's changing, and also the hydrosphere. And we'll take a look at the impacts of that change on humans, particular changes in ecosystem functions and subsequent changes to human well-being criteria. And then finally, we'll take a look at some of the responses briefly. All right, so first of all, global climate change. What is it? It's one of the largest impacts humans are having on their environment. Okay, it's caused by decades, if not hundreds of years of pollution. So that pollution is mainly pollution of the atmosphere. So humans are having a global impact on their environment for the first time through this pollution of the atmosphere. Unfortunately, there tends to be widespread denial of what is happening, not only due to vested economic and cultural interests in preserving current use of resources and current rates of pollution, but also because of denialism in terms of how can humans be causing such a huge impact on the environment. It has previously been inconceivable or just simply unimaginable that such changes in the environment, the global environment, could be caused by people. Up until now, effects by people have really only been local or regional, but now with global climate change, we're seeing something which is truly global in scope. So what is happening, or what humans are doing in New York, for instance, is having an impact on what's happening in Antarctica. So emissions of carbon into the atmosphere in the urban regions of New York are causing the atmosphere to warm and melting glaciers in Antarctica. So some people just cannot get their head around humans are able to do this. But it's certainly scientifically very feasible, and it is happening now today. Okay, but it's not just caused by somebody driving their car from home to work in New York over the course of a day. No, but this is caused by decades, if not hundreds of years, of air pollution building up in the atmosphere. Predictions of what will happen have been made and are becoming more accurate each year. Now, the predictions of what will happen in the future are being made by using modeling. So what scientists are doing is they're using physics and mathematics in global circulation models to best understand what will happen to the atmosphere as CO2 and other greenhouse gases rise in it. In other words, as the pollution of the atmosphere increases, scientists can use mathematics and physics to predict what will happen to that atmosphere. And the other important part of these predictions is that scientists are improving them year after year because they are able to take the past trends in things like temperature of the atmosphere or changes in circulation of air around the world and currents in the oceans and so on, ocean temperatures and so on. They can look at past changes from, say, the 1950s, 1960s, 1970s, and they can see how changes in CO2 in the atmosphere or changes in pollution in the atmosphere change with the temperatures and so on of the atmosphere and the hydrosphere. And as we get more and more data after, say, 5 years after the last set of data was used to predict or construct a model, we get five years more data, and we can construct an even more accurate model. And these models are becoming more and more accurate each rounds in which new data comes in. And these predictions are what scientists use to understand how global temperatures and global circulation models will change as more and more pollution is added to the atmosphere of the Earth. And in particular, the greenhouse gases are added to the atmosphere of the Earth. So these atmosphere-hydrosphere systems are very complex and very difficult to model. So as time goes on and as more data is gathered, the predictions become more and more accurate. And what they're looking at today is we are looking at an increase in the atmospheric temperatures. All right, so what's causing all of this pollution? These are the drivers which are causing atmospheric pollution, which is causing in turn the changes in temperature of the atmosphere and the hydrosphere. So what are the drivers? Ultimately, it's the usual increase in human populations and increase in GDP. Okay? So increase in human populations and increase in GDP mean that there is an increased demand in terms of human population for energy. And because human technology is very energy intensive nowadays, ever since the ever since the Industrial Revolution, where coal was first used to drive machinery, which allowed factories to be created to create more and more cultural items like clothes and steel and so on. Those energy uses for this increased technology has been baked into societies, global societies around the world today. They're baked in because they are required not only to produce the technology which allows a certain standard of living and allows the current structuring of society, but those energy-intensive technologies are also critical for intensive agriculture, which the world relies upon to feed the vast numbers of people now. So if we didn't use this energy to drive the intensive agriculture and to drive the technological development behind it, we would have mass starvation of people. And nobody wants that to happen. So we are left with this increase in pollution caused by the technologies which require a lot of energy, and that energy is gained from fossil fuels, coal, natural gas, and oil, and that is the main reason why we are polluting our atmosphere, because in obtaining the energy from these sources, we are transferring carbon from the geosphere, from rocks, into the atmosphere. Okay? So by burning coal, gas, and oil, we are transferring carbon from the geosphere, from rocks, into the atmosphere. Now, carbon, as we'll go into in a little minute, is a very important molecule because it forms carbon dioxide, which is a molecule, due to its physics, it traps and holds heat in its gaseous form. And simply put, if you have more carbon dioxide in the atmosphere, the capacity of the atmosphere to hold heat is increased. Okay? Also, we have changes in land use by humans as we clear land for agriculture. That actually transfers carbon from the biosphere into the atmosphere. So the biosphere would mainly be vegetation. That's the vast majority of the biomass in the biosphere. And the vast majority of biomass in vegetation are in forests. As forests are cleared and burnt, the trees are burnt, then the carbon in that forest is transferred into the atmosphere. And land use change from woodlands and forests into agricultural systems, which are usually cleared areas where they plant short-term crops, increases or releases a lot of carbon from the biosphere into the atmosphere. So two main ways in which human activities are transferring carbon into the atmosphere and essentially polluting that atmosphere. Okay? So humans polluted the atmosphere before, but up until the 1700s, up until the industrial and agricultural revolutions, the effects were mainly local. But after the first industrial revolutions in Western Europe, the industrial revolutions and the ability to manufacture goods and so on spread throughout the world. So we would have manufacturing throughout the world. In the New World, in North America, Canada, also down into Central America, South America, all throughout Asia, China, Japan, Southeast Asia, Australia, everywhere has industrialized. Because of this industrialization, energy-intensive technologies have proliferated, and therefore use of coal, oil, and gas has ramped up dramatically, and we'll see just how much in a minute. Agriculture also uses a lot of energy, but it also produces a lot of methane. Methane is also a greenhouse gas, and it is even more of a potent greenhouse gas than CO2. However, the amount of methane which is produced is much less than CO2. So methane, even though it does cause a fairly large proportion of global warming, it is still CO2 which is causing the majority of it. Okay? Production of concrete. Concrete is really one of the main building blocks of urban and industrial landscapes. Concrete is one of the simplest, cheapest ways of building very large buildings and structures, but it is also a very potent source of CO2. Concrete is derived from limestone. Limestone is calcium carbonate, and how concrete is produced is by heating it up and converting it into calcium oxide and CO2. So the calcium carbonate converts or reacts in the process of heat into calcium oxide, which is the quicklime, which is used for concrete, and CO2. So every time you produce concrete, you're producing CO2, but not only directly from the reaction, but also in the heat or the energy used to heat up the limestone to drive off the CO2 to get the quicklime, which can be used for concrete. Okay, so concrete is also another fairly substantial, much lower than land use change or energy inputs to pollute the atmosphere, but concrete is still a fairly substantial part of the pollution problem around the world today. All right, so let's take a look at how the pollution has ramped up over time. Okay, as you can see, in the 1800s, the vast majority of human emissions, energy consumption was traditional biofuels. So that would have been firewood or charcoal. Around about the Industrial Revolution, around the 1850s or so, coal became more and more important. It became the primary source of energy for industrial applications and for powering agricultural machinery. Okay, up until the early 1900s, about the 1920s, 1930s, and all through, and it ramped up massively during World War II, and then into the 1950s, crude oil became one of the main sources of energy for people. At the same time, natural gas also became very important. So the three big fossil fuels, coal, crude oil, and natural gas, form the vast majority of fuel used by people. Traditional biofuels, although it does pollute, in its manufacture, which is basically growing plant material, trees maybe for wood, carbon is taken out of the atmosphere. So traditional biofuels, when you look at it in a net way, carbon is used, taken out of the atmosphere for its production, and then released back into the atmosphere. So traditional biofuels tend not to pollute the atmosphere when you look at it in a holistic sense. However, coal, crude oil, and natural gas, because you're burning what is essentially a rock, it transfers carbon from the geosphere or the lithosphere into the atmosphere. Okay? So that's with global energy consumption, and this is the main way in which humans pollute the atmosphere. Moving on to land use now. As you can see, land use has changed over time from around the period of 2,000 years ago, around the birth of Christ. We've seen a massive increase in agriculture. Okay, so grazing and cropland from around the 1700s, 1750s, 1800s, grazing and cropland have just taken off and massively increased, particularly grazing areas. Okay, grazing areas would be for cattle production, for producing meat. Okay, so human population growth has driven much of this change, but also adoption of energy-intensive technologies also increases these pollution of the atmosphere. And as I said before, this change in land use induces a transfer of carbon from the biosphere into the lithosphere, into the atmosphere. Okay? So with an increase in grazing, there's going to be a reduction in trees, and that's going to mean a transfer of carbon into the atmosphere. Okay, so any sort of change in land use from forests into agriculture will mean an increase in pollution of the atmosphere with carbon dioxide, which is the greenhouse gas. Okay, so just to give you an idea of how land use has changed, or what the status of land use is at the moment around the world. If we look at the Earth's surface, 29% of it, the Earth's surface, is land, and 71% is ocean. Okay, so we work with the land surface. All right, of that 29% of the surface of the Earth, which is land, of the land, 71% is habitable land, and 10% is covered by glaciers and is otherwise unfit for habitation. Maybe deserts, or it may be just completely degraded and unusable by humans for their activities. 71% of land, however, is habitable. Of that 71% of habitable land, 50% is devoted to agriculture, and almost 50% is devoted to forests and shrublands, or natural ecosystems. About 1% is devoted to urban areas, and 1% is under freshwater lakes. Okay? So the habitable land on the Earth is divided up between agriculture. About 50% of it is under agriculture now, and 37% is under forests and 11% is under shrublands, which are more or less natural ecosystems. Okay? If we look at the agriculture part of the habitable land, okay, and 50% is agriculture, so 50% is causing pollution of carbon dioxide into the atmosphere. Of that agricultural land, 77% of it is under grazing, so that's livestock, meat and dairy production, and 23% is under crops. Now, if we look at what humans get from livestock and what they get from crops, we'll see when it comes to the calorie supplies, 82% of the calories for humans comes from plant-based. So this 22% of the area accounts for 82% of the human's calories. Okay? And meat only supplies about 18%. So that calorie supply, okay, from meat comes from a much, much wider area of land. So if we wanted to reduce our area under agriculture and still feed our people, we would need to reduce the amount of livestock, the amount of meat that people eat. Okay? People would say that we need our protein from meat, but actually 63% of our protein comes from plant-based foods, so the legumes and so on, which form proteins. And only 37% of our protein comes from meat. So if we increased our croplands, we could increase the amount of proteins that we get, and we could probably reduce that proportion of meat use quite dramatically. Okay? If we did that, we could decrease our agricultural area, increase our forest area, and reduce the pollution of carbon dioxide in the atmosphere. Okay? And that would mean a cultural change. It's a real thing, it could happen, but it's probably more likely that this 50% figure will remain the same, and that the additional numbers of people which are populating the earth as population grows will instead be accommodated by increasing cropping areas and reducing livestock areas, so that the amount of calories which are available to people increases. Okay? All right, so that's the state of the situation at the moment. We've got a lot of energy-intensive technologies supporting a larger population of the Earth and also supporting a higher GDP or standard of living for those people. Okay? As population gets bigger, we need more energy use, and therefore we pollute the atmosphere more, and there tends to be more carbon dioxide in the atmosphere. And we'll take a look at that now. So what are some of the pressures caused by by increases in humans' emissions? Well, levels of carbon dioxide, methane and nitrous oxide have increased due to agricultural intensification and industrialization. So with increases in human emissions, we've got increases in these gases. Okay, we've got increases in other gases as well, but these are the main ones, the important ones for global climate change. As the levels of these gases increase in the atmosphere, we get a warmer atmosphere and also a warmer hydrosphere. Why is that? Because carbon dioxide, methane and nitrous oxide absorb heat in the atmosphere and allows the atmosphere to hold more heat, and that heat would otherwise be reflected back out into space, but it's held there. So this is known as the greenhouse effect. And the greenhouse effect is actually very important, and it does allow life on Earth. If we didn't have carbon dioxide in the atmosphere, then much of the heat from the sun would hit the Earth and bounce straight off, and we would be much cooler than we are now. Okay? And that would probably mean that life on Earth, as we know it at least, would probably not be possible. So we do need some greenhouse effect. However, the problem comes when we have an increase in that greenhouse effect, and therefore an increase in temperature. Okay? And that changes things, and we'll talk more about that in a minute. Okay? The Earth is on a very fine balance. If we just change it a little bit, then the changes can be profound in other parts of the world. Okay? So this process where these molecules absorb heat in the atmosphere and allow it to hold more heat is known as radiative forcing. And each gas increases the temperature a different amount per concentration of that gas in the atmosphere. So 1 unit or 1 liter of CO2 may increase the ability of the atmosphere to hold heat to a certain amount. Okay? 1 liter of methane increases the ability of the atmosphere to hold heat to a greater extent than, say, 1 liter of carbon dioxide. But unfortunately, the amount of carbon dioxide which is being produced by humans through land use change and through burning fossil fuels to create energy to drive the technologies which keep the world going now, or human society going, means that there are massive amounts of carbon dioxide being pumped into the atmosphere every day all around the world. Okay? So the carbon dioxide pumped into the atmosphere allows the temperature of the atmosphere to increase through radiative forcing. Okay? And the end result is an increase in the average temperature of the atmosphere and also the hydrosphere. Okay? Even small changes in this temperature will induce big changes in the way that air and water circulate around the Earth. Okay? And those changes in the way that air and moisture circulates around the Earth are going to be fundamental to the effects that global climate change will have on people around the world. All right, so looking at some graphics here, just giving you an idea of the amount of change or the amount of pollution which has gone into the atmosphere by humans since the start of the industrialization and intensive agriculture. At the time, it was around 200 ppm. The concentration in 1995 rose to 360 ppm. And nowadays, I think in 2018, it had actually risen above 400 ppm for the first time. So the amount of carbon has increased by well over 30% now. And most of that is due to burning of fossil fuels, deforestation and land use change. Okay. Methane is also increased, okay, but by the amount of methane is increased by much smaller amount by the amount of carbon dioxide, that is. But that's a good thing because methane is an even more potent greenhouse gas, but because there's less of it, it has less of an effect. Even so, the amount of methane that has increased in the atmosphere is by about 143%, which is much greater than the increase in the amount of carbon dioxide. But because there is more carbon dioxide, this means more than this. This increase in methane is reflected by an increase in agriculture a lot of the time. Cattle refuse landfills, rice cultivation, and also in biomass burning. Methane is also accidentally released when fossil fuels are extracted from rocks, and that causes a lot of methane to escape into the atmosphere and cause this extra pollution in the atmosphere. Nitrous oxide has also increased by about 11%. That is also a fairly potent greenhouse gas and does contribute to global warming, but its contribution is very much dwarfed by methane and carbon dioxide. All right, so this graphic gives you an idea of how the greenhouse effect works. The sun is our source of energy on Earth. We don't get energy from anywhere else but the sun, except for radioactivity in the Earth's surface, and that's what drives volcanoes and also some hydrothermal sources of energy. But the vast majority of energy which humans use comes either directly or indirectly from the sun. Directly from the sun, we can use solar panels and so on to capture it. Indirectly, we use coal, gas, and oil. So these are plant materials which have been effectively fossilized and incorporated into the geosphere as rocks, and they are then burnt. Okay? At the moment, any light which comes from the sun or energy which comes from the sun now and hits the Earth is either absorbed by the surface, and that absorption could be in the form of heat, heating up the ground, or it could be taken up by the biosphere as the plants photosynthesize. So a fairly large amount is absorbed by the surface, and of that amount which is absorbed by the surface, a large proportion of it is reflected back out into space as infrared radiation. Okay? Now that infrared radiation, as it travels out through the atmosphere, okay, most of it just passes straight through the atmosphere, but some of it is absorbed. And it's the amount which is absorbed mainly by carbon dioxide, but also by methane and nitrous oxide and ozone. That amount which is absorbed causes an increase in the temperature of the atmosphere. Okay? So the amount of infrared radiation which is absorbed by the atmosphere increases when we have increased amounts of greenhouse gases. And that is what increases the temperature of the atmosphere. Okay? Now, as I've said, different gases have different contributions to global warming, and this graphic shows some of the contributions of the different gases. As you can see, we were talking about radiative forcing. How much radiative forcing or increases in temperature are due to the different gases. Okay, as you can see, CO2 has the greatest contribution to global warming. Okay, so the spatial scale is global and the impact is very high. Okay, methane, nitrous oxide, and halocarbons, which would be things like chlorofluorocarbons and so on, which are being phased out because they're bad for ozone up in the ozone layer. They also form a fairly large whack of greenhouse gases. Okay? And these types of greenhouse gases accumulate in the atmosphere. They don't break down. So once they're in the atmosphere, they stay in the atmosphere. So they are long-lived greenhouse gases. And they cause a large amount of increase in the temperature of the atmosphere and also the hydrosphere. Okay, but as you can see, CO2 is the king. Methane is probably about a fifth of that, and then N2 and the other halocarbons are another fifth or another quarter again on top of CO2. Okay, so these are the gases which are most responsible for global climate change. All right, so what is the state of the atmosphere and the hydrosphere at this moment in time? And how are they changing? Okay, so first of all, the atmosphere. We are most interested in these things: the chemical composition, the temperature, the way that gas circulates around in the atmosphere, or the wind, and the way water circulates around in the atmosphere. Okay, so these are the things which we are most interested in, mainly because these are the things which impact on our ecosystem services the most. Okay, so the chemical composition of the atmosphere is changing. We have increases in CO2, methane, and nitrous oxide, and also the fluorocarbons as well. Okay, as we've seen, that this change in chemical composition of the atmosphere causes an increase in temperature in the atmosphere through radiative forcing, as the atmosphere is able now to absorb more heat. So the surface temperature of the Earth is increased, but the changes tend to be unevenly distributed. So some parts of the Earth heat up more than others, and we'll take a look at that in a minute. Generally, it's the temperate regions of the Earth which show a greater increase in average temperature, particularly the Arctic regions of the Earth. So what we're seeing is basically a evening out of temperature across the surface of the Earth. So the tropics is increasing in temperature, but by not as much as, say, the Arctic areas of the Earth and the temperate areas of the Earth. Okay? We are seeing the largest increases in temperature in the Arctic and the lowest increases in temperature in places like the tropics. Okay? That's probably due to do with several factors, mainly because heat, which is captured in the tropics, is transferred throughout the world. Okay? All right, wind circulation. Wind circulations are changed as pressure system patterns change and winds start to get stronger. As we get more energy into the atmosphere, and increased temperature is a reflection of more energy, the winds will get stronger. We will get stronger gradients between high pressure systems and low pressure systems. and therefore winds flowing between them will increase and become much stronger. Okay, so wind circulations change, but also pressure systems will change as the temperatures on the different parts of the earth begin to equalize or become less different. Then we will start to get differences in the way that the gases on the surface of the earth circulate. I don't think we're going to see huge, massive changes, but even the smaller adjustments to wind circulation systems will have big impacts on ecosystem services which humans use. As wind circulation changes, moisture circulation changes. Okay, so the moisture circulation will change as temperature increases and wind patterns change. So clouds will be blown around in different patterns. And that means that we will start to get different patterns of rainfall. Okay? So places like, for instance, Mediterranean regions, at the moment, they get most of their rainfall during the winter when predominantly easterly blowing winds, or winds coming from the west and blowing to the east, come from the north and bring moisture down as rainfall along from the northwest. Okay, these Mediterranean regions, however, as they heat up, that moisture or those winds are less likely to track as far south to reach the Mediterranean regions. And so therefore the Mediterranean regions are less likely to get as much rainfall in winter. And we're actually seeing that today. The past 20 years have been some of the driest on record for the Mediterranean ecosystems around the world. So in the true Mediterranean, around the Mediterranean Sea, seen a drop in rainfall. Seen a drop in rainfall in California, which is a Mediterranean climate. We've seen a drop in rainfall in southwest Australia, which is also a Mediterranean ecosystem. Okay? So these changes in rainfall obviously are going to have a big change in the ecosystem services. So rainfall or precipitation distribution and seasonality will change as moisture circulation changes, precipitation patterns and seasonality changes. Some places will actually get more rain and some will get less. So this year, Eastern Africa had massive amounts of rainfall, which caused a lot of flooding. Okay? At the same time, places like the western coast of Australia had less rainfall than it usually does. Okay? So just to prove to you that carbon dioxide levels are changing, this is a pattern of changes in carbon dioxide levels over time, going from about 800,000 years ago up to the present day. Okay, so these carbon dioxide concentrations would have been derived from little air bubble inclusions in ice cores which have been drilled from the Arctic and the Antarctic. As snow falls, it traps air beneath it, and as it is compacted down into ice, those air bubbles are trapped and kept, and they form a record of what the composition of the gases of the atmosphere were at that particular time when they were laid down. So if you drill a core down 2 or 3 kilometers into the glaciers in Greenland and Antarctica, you will get a record of what the composition, the gas composition of the atmosphere was like 800,000 years ago. And as you can see, over time, the amount of carbon dioxide has fluctuated. It has gone down, come up, gone down, come up, gone down, come up, and so on, in a sort of regular cycle, until we reach close on today, where it has just taken off out of the range of the cycling for the past 800,000 years. Okay? And this is where humans started burning fossil fuels. Okay? It's thought that the changes in carbon dioxide reflect wobbles in the Earth's atmosphere, in the Earth's rotation around the sun, which will increase or decrease the amount of energy entering the atmosphere. And this will in turn cause ice ages. Now, these ice ages will increase or decrease the amount of photosynthesis, and therefore increase the amount of carbon being pulled out of the atmosphere by the biosphere. So when we have the onset of an ice age, photosynthesis falls dramatically and the amount of carbon dioxide entering the atmosphere goes up. And then gradually over time, as the world readjusts, the amount of carbon is extracted, and as the Earth warms up again, then the amount of carbon is taken out of the atmosphere. Okay, so these cycles are due to changes in Earth's temperature due to wobbling of the Earth, basically, as it orbits around the sun. What has happened here, though, is we have busted out of this cycle. And because we have massively increased the amount of carbon dioxide in the atmosphere, we have massively increased its ability to hold heat. And because of that, the wobbles in the atmosphere no longer matter so much. So because of that, we are not getting ice ages again. We were probably due for a next ice age, but that has probably been postponed now or cancelled because of the amount of carbon dioxide in the atmosphere. Okay? All right, so with the changes in carbon dioxide, we get a change in temperature. And as you can see, around 1850, temperatures were lower than a baseline which was taken around, I guess, around World War II, or some baseline which was set at around 1940 or 1960 or something like that. Temperatures have risen consistently since the 1920s. They've gone up until they've reached almost around 0.6 to 0.8 degrees above what they were around World War II. Okay? So this increase in temperature is different in different parts of the world. If you go to this website, Our World in Data, they actually have this graph for the northern hemisphere and also for the southern hemisphere. And we can see that in the northern hemisphere, temperatures have increased by almost up to 1 degree centigrade. So it's much higher than the entire global average. And the southern hemisphere has increased by about 0.6. And the equator is about the same as we see here as the global average. Okay, so the amount of temperature is definitely going up. for the atmosphere. And that is reflected quite well in the increase in the amount of carbon dioxide in the atmosphere. Okay, so temperature is increasing as the chemistry of the atmosphere changes. We would also get changes in the way that the air circulates around the world. At the moment, you probably all recognize this model of how air circulates around the world. Around the equator, we have the highest amount of energy hitting the Earth, and therefore air heats up and rises and travels at a high altitude before it begins to cool down and descend once again. Okay, so at the equator, the hot air rises, moves across, and then comes back across the surface of the Earth. Okay, so the hot air rising at the equator and is also accompanied by lots of thunderstorms and precipitation. And the cool air descending at the about 30 degrees latitude and longitude, so latitude and longitude, Tropic of Capricorn, Tropic of Cancer. These aren't actually the tropics. This is 30 degrees north and 30 degrees south. The tropics are more to the south around here. You would get high pressure systems as the air descends. And these high pressure systems, because it's descending air, basically is very dry. So this is where you would get deserts around the world. Okay? If we were looking at Africa, we would be looking at the Sahara Desert. Okay? All right, so these moisture patterns are very much reliant on how the air circulates around the world. At the moment, the wettest part is at the equator. Okay? The next wettest part is at the middle latitudes, where we get a certain amount of heating and rising of air, but also westerly winds bringing moisture in. All right, so these trade winds which blow from the east as a result of the Hadley cell mean that we get more rainfall on the eastern edges of continents and the eastern sides of islands. But once we get beyond about 40 degrees north of the equator, about 30 degrees north of the equator, the winds will tend to come mainly from the west. Okay? They will come from the west, and that means we will get more rainfall on the western sides of continents. As the temperature of the atmosphere changes, these circulation systems are likely to also change, and that is going to mean a change in the distribution of rainfall. Okay. All right, yes, I put this one in here because it's not just that very simplistic view of how air moves around the world, which is important. We also have influences on things like pressure systems in continents, but also seasonal movements of these circulation systems. And in particular, around the tropical regions, the movement of the Intertropical Convergence zone. So this is where the majority of the heat from the sun heats up the atmosphere, causes air to rise, and causes rainfall. Okay? In the summertime, in the southern hemisphere, then this zone, which gets the most heat, is in the southern hemisphere. In the summertime, in the northern hemisphere, June to August, this zone is up in the northern hemisphere. And because this is an area where the air is being heated up and forced to rise, it is a low pressure system, so winds will always blow towards it. Okay? Now, there are parts of the earth where they have these things called monsoon rains. You've all heard of monsoons. That is when during the wet season, you would tend to get more rainfall. So you would have monsoon rains. In India, the ITCZ forms across much of India during the wet season. This would be June to August, and winds, to the trade winds, which would stream towards this low pressure zone, but they would hit the equator, and through the Coriolis effect, they would bend back round into the low pressure system. Now, this is quite important for the west coast of India here, because as I've said before, it tends to be the east coast of continents and so on which get most rainfall. But because of this monsoon bending of the trade winds across the equator during July and August, at the eastern part of India gets a lot of rainfall. So for the eastern part of India, these local effects or regional effects of the Coriolis effect, bending the trade winds during exactly the right time of year, means that the eastern side of India gets a lot of rainfall. Okay, so instead of that very generalized pattern of how winds blow, we will get complications in those patterns due to local and regional effects. Okay, and that means that how rainfall, precipitation amounts change across the earth is very complicated and fairly difficult to model. All of these things need to be taken into account. Okay? At the moment, what seems to be happening is that the monsoon tends to be weakened by increase in temperature, and the whole trade wind system tends to be disrupted because of the increases in temperature. With a disruption of that trade wind system, you're going to get less monsoon rains on the eastern coast of India. So you may actually get droughts in India because of global climate change. Similarly, Australia would suffer in the same way, because northern Australia is supposed to get a monsoon during the wet season in a similar sort of way to India. So global climate change will actually cause more droughts in northern Australia and eastern India compared to what happens today with the monsoons. All right, so I've explained this to you to let you know that increasing temperatures will change the distribution of wind patterns, and that will change the patterns of rainfall, but it's not as straightforward as it immediately appears. Some places which you would expect to get more rainfall actually don't, and actually get less rainfall, okay, for various local and regional effects. Okay. All right, so at the moment, the average annual rainfall around the world, as I said, is concentrated in the equatorial regions. That's where we get the most rainfall. Other than that, another general pattern is that at least up until 30 degrees north of the equator, we would get the majority of rainfall on the eastern sides of continents. Okay? And on the western sides of continents, up to about 30 degrees, we would get deserts. So the Californian deserts, the Saharan deserts, the Arabian Peninsula, and so on. Okay? And then in the southern hemisphere, we would get the Atacama deserts in Chile, the Kalahari in southern Africa, and the Australian deserts that we all know about. Okay? And these patterns of rainfall may change, and we would get wetter areas on the eastern sides of the Indian Peninsula because of that monsoon effect and that bending of the Coriolis bending of the trade winds as they cross the equator, and they're deflected by the spinning of the earth. Okay? Could be that this supply of rainfall on the eastern side of these peninsulas will be reduced as trade winds begin to break down. So what does that mean for changes in precipitation? When we do the modeling using global circulation models, which is basically, as I said, physics and mathematics to determine fluid dynamics in the atmosphere and in the hydrosphere, we come up with these predictions for the amount of rainfall in an area compared to what it is today. So the brown tones are negative, so they're a fall in rainfall by the end of the 21st century. So that's 2100. And the blue tones are positive, so an increase in rainfall. So generally we're seeing an increase in rainfall on the equatorial regions, and in particular the western part of the equatorial regions, but it's not consistent across the way. Okay? Many parts of West Africa, it looks like they are fated to have a big decrease in rainfall. And that's probably because the monsoons are decreasing. Northern India, also a big decrease in rainfall. Okay. Eastern India, though, seems to be okay. It's got a slight increase in rainfall. Australia is going to suffer a lot, and the Mediterranean, as I said, suffering a lot. Okay. If we can close in on the Caribbean, not a great slide, I'm sorry. These are 4 different models of how it's expected precipitation will change over time. This model predicts if we manage to reduce our CO2 emissions, to keep the global temperature to at 1.5 degrees centigrade. This one is if we manage to keep increases in global temperature to 2 degrees and 2.5 degrees. Okay? If we manage to keep it down to 1.5 degrees, this is Trinidad here, this is Cuba, Hispaniola, the Lesser and Greater Antilles here, and then Trinidad down here. It seems like Trinidad is looking to lose rainfall share, probably because of that reduction in the trade winds that we would see during the monsoons. The higher the temperature is allowed to get in the atmosphere, the more intense the reduction in the share of rainfall for Trinidad and the southeastern Caribbean, probably also for much of the Lesser Antilles as well. Okay, so Trinidad is most likely to have a reduction in the amount of rainfall throughout the year. Are we prepared for that? So let's move on now from the atmosphere to the hydrosphere. What is going to happen with the hydrosphere? And what is the status of the hydrosphere? Chemical composition, temperature, mixing of the water column, and current circulation. Okay. Chemical composition of the hydrosphere. Increases in CO2 will mean in the atmosphere will cause more CO2 dissolved in the water of the oceans. This is going to change into carbonic acid, a weak carbonic acid, and depress the pH of the oceans overall. Okay, so this is going to mean a acidification of the oceans as more carbon dioxide is dissolved in the water, and that increased carbon dioxide comes from the atmosphere. At the same time, there will be a decrease in oxygen because temperature of the water is increasing. As water temperature increases, it is less able to hold dissolved oxygen. So that means the composition of oxygen in the oceans will decrease as they get warmer. Okay? So the two big impacts with global climate change will be an increase in CO2 dissolved in water, which will depress the pH and acidify the oceans. The increase in temperature will also decrease the amount of oxygen which the oceans can hold, and that's going to have implications for the majority of sea life, because sea life requires oxygen to live and move around, or at least the animals do. All right, so chemical composition will change, temperature will increase, and that will lead to thermal expansion of the ocean. So as water temperature increases, if something heats up, it expands. And we are going to see sea level rises based on thermal expansion. As temperatures rise, we will see a melting of continental ice sheets. Now, melting of continental ice sheets means that water, which wasn't in the ocean, it was actually perched up on the land. So it's like an ice cube has been placed on land, and then it melts, and all the water from that ice cube runs down rivers and streams and into the ocean. So all of that water, which was originally in a glacier, is now contributing to the volume in the ocean. And that is also going to increase the sea level. Okay, so temperature has a double effect to increase sea level. One is thermal expansion, and the other one is melting of continental ice sheets, which will then put more water into the ocean and cause sea levels to rise. Okay. We're also going to get changes in mixing in the water column. Changes in wind patterns and ocean currents will cause more or less mixing in the water column, and that is going to have positive or negative effects in the amount of CO2 in the atmosphere and also in the oceans. And we'll talk more about that in just a minute. Current circulations may also change. At the moment, many of the ocean's currents are driven by a seasonal increase and decrease in salinity in oceans in the Arctic and Antarctic regions, where ice caps either freeze or melt. And that change in salinity means that bodies of water will become more and less dense. Okay? So when there's more salinity, when it's less salinity, the oceans will become less dense. When there's more salinity, when the ice freezes, okay, and fresh water is taken out, because when water freezes, the salinity, the salt doesn't freeze with the water. Okay, the remaining water becomes more saline and sinks. Okay, as it sinks, it causes a depression in the surface of the ocean, so currents will bring water in to replace that water which is sinking, and that drives ocean currents. So for instance, up in the North Atlantic around Iceland, between Iceland and Greenland and to the north of Iceland, every year ice forms, icebergs form floating on the ocean. And that means a large amount of water actually sinks there. And that pulls water up from the south, from the equatorial regions. And that water tends to be warm. Okay? So we have this current called the Gulf Stream, where water is pulled up from down by Florida and the Caribbean, up the eastern edge of the United States, and up into northern Europe. Okay? If that pattern, that seasonal freezing of the ocean and the formation of the ice cap in the Arctic begins to break down, the Gulf Stream will begin to weaken, and that will mean a change in current circulation. And that will have all sorts of implications for climates and so on, particularly in Eastern Europe. All right, so a few infographics to show you how the hydrosphere will change. The amount of carbon in the oceans is mainly held in the deep oceans as stable forms of carbon, either sediments or caltrates, which is a solid, which is just sits at the bottom of the ocean. Okay, that does interact with the water column, so some comes in and some comes out, and we have a stasis between the atmosphere and the oceans. So as CO2 dissolves in the oceans and then is emitted back into the atmosphere. At the same time, we would have an exchange of carbon from the ocean surface down into the deep ocean in these stores, and then back out again. Okay? We also have a migration of carbon from the marine biota into the ocean, free ocean again, and then back into the marine biota. Okay? All right, so carbon, there is a fair amount of carbon in the oceans, mainly down in this deep ocean store. Now, this carbon will tend to be released and sequestered based on movements of water in the water column. Okay? Down at the bottom of the oceans, carbon will tend to be held there. And quite often, if a carbon gets down below 1,000 meters, it's not going to come back out again for over 1,000 years. Okay? And the deeper you go, the longer it's going to be sequestered down there. Okay? If the carbon is down around about between 3 to 1,000 meters, it's not likely to come back out to the atmosphere for another 100 years. And around about 100 to 300 meters, it circulates every about 10 years or so. Okay? That's gaseous carbon dissolved in the ocean. When it comes to organic carbon, the majority of the organic carbon is in the surface of the ocean, but as things die, quite often bodies and skeletons will fall to the bottom of the ocean. And once they fall down to the smaller layers of the ocean, or the lower layers of the ocean, they tend to stay there. Okay? There tends to be a lot more mixing of the surface waters than there is down below. So the energy of storms and hurricanes and things really only reach down about for a few 100 meters. Okay? Once you get beyond about 1,000 meters, there's not very much mixing. So if carbon, either dissolved as carbon dioxide or in particles, reaches below 1,000 meters, it generally tends to stay down there for millennia. Okay? And it's only in the big oceanic currents where you get an upwelling of deep water to the surface again, and that's specific parts of the ocean that we will start to get carbon coming out again. Okay? All right, so this infographic talks about how pH, or the acidification of the oceans over time. Okay? Here we can see the atmospheric concentration of CO2, which is the red line. It has gone from about 310 around 1955 all the way up to over 400 around 2018. In response, the seawater CO2 has increased over time. Okay, so the amount of CO2 dissolved in seawater increases as the concentration of CO2 in the atmosphere increases. And as the concentration of CO2 in the seawater increases, so the amount of CO2 breaking down into carbonic acid by reacting with the water molecules causes the pH to fall. Okay, so as concentration of CO2 in the water column goes up, the pH of the oceans go down. Okay, now this is actually a big problem because many creatures in the ocean, they rely on calcite or calcium carbonate to produce their skeletons, which are usually exoskeletons. So the vast majority of shells are made by calcium carbonate. When you get an increased amount of hydrogen ions, which you would with a low pH or more acidic solution, those hydrogen ions react with the calcium carbonate to form water and reacts with the calcium carbonate to break it down into quicklime, into that calcium oxide, which is not a hard substance at all. It's not an insoluble substance at all. So skeletons and shells will begin to weaken. So that means coral reefs are less able to grow, and other animals are less able to form their skeletons. Okay, so we have a situation where decreasing pH is going to have big impacts on ecosystems like coral reefs. Okay, all right, with the change in oxygen, okay, we've seen oxygen is decreasing since the 1900s to the 2000s. Oxygen has decreased, and now it's predicted to decrease even further. Oxygen is very important for animals. When we don't have oxygen, it tends to mean that there are less fish and plants in the oceans. So oxygen supports abundant sea life. Less oxygen keeps fish and plants away. And we're going to have less oxygen as the temperatures of the oceans rise. When the temperatures of the oceans are higher, that means the water is less able to hold oxygen, and therefore we will get breakdowns in these abundant marine ecosystems. Okay. All right, and this is where I was talking about these global circulation currents in the oceans and how they change. See, the Gulf Stream is pulled up as we would get ice forming in the North Atlantic up here, and the water is pulled up, okay, and the saline water which forms sinks down to the bottom of the ocean and flows down at the bottom of the ocean down further south. Okay, so we would get the Gulf Stream, which has an important impact on the climates of the eastern United States and Canada and northern Europe. Okay, once those systems begin to break down, we get big changes. Oh, and one local example of currents changing, causing an impact, is with the Sargassum Seaweed. Okay, at the moment, these are the main currents around the Atlantic, the central Atlantic, and the Caribbean. Okay, we would get the south equatorial current flowing through across the northern part of South America, up into the Caribbean, back out past Florida, up through the Gulf Stream and up into the North Atlantic. We would also get smaller currents forming around the equator, and in particular we get a circular current called the North Atlantic Recirculation region, which forms around the equator. We also get a current going around in a circle from the Gulf Stream, heading down into the Atlantic and then back around towards Florida. And we'll get a loop in a current there. Okay? This, and coupled with an area of fairly low wind speed, causes the Sargasso Sea to form. Sargasso Sea is characterized by lots of floating Sargassum Seaweed, and they float there because they are trapped. They can't flow anywhere because they're in the middle of this circulation of water, and so they're kept in a fairly compact system. Okay, and this is historical. You've all heard of the Sargasso Sea and how it forms and characterized by loads of seaweed. Okay, this circulation has previously been much weaker, but with global climate change, it's thought that it has become a lot stronger, and that means within this circulation, or gyre as it's called, you're starting to get conditions which are very similar, which occur with the Sargasso Sea, and therefore the growth of a lot of Sargassum seaweed. So you're starting to get large clumps and patches of Sargassum seaweed forming when the conditions are right in the middle of this circulation current, which is becoming more and more frequent and stronger with global climate change. So how does that affect us? Well, what it means is that the Sargassum seaweed, when it does escape from this area, is carried by the South Equatorial Current past Trinidad, through the Lesser Antilles and up into the Caribbean. And all of that seaweed that we start to see washing up on the beaches of the Lesser Antilles and Trinidad, which is a big shock to everybody and a big threat to the tourist trade in the Lesser Antilles and also in Trinidad, all comes from this newly strengthened North Atlantic recirculation region. And because it's more strengthened, then Sargasso seaweed is given more chance to grow, and therefore there are greater inputs of that Sargassum seaweed into the Eastern Caribbean, which is causing that big problem. So all of this is to do with global climate change, heating up, and an increase in strength in this ocean current. Okay, so that's one example, a fairly nice example of how changes in ocean currents are causing changes in ecosystem services in different parts of the world. Okay, all right, so that's what I want to move on to now, impacts of these global climate change things on ecosystem services and human well-being. So we've got our normal ecosystem services, our supporting services, so things like nutrient cycling, air and water circulation. Got our provisioning ecosystem services, which would be food, wild and agricultural, water production, excuse me, fuel wood, charcoal and medicines. We've got our regulating ecosystem services, carbon sequestration, natural disaster protection, pollination, soil degradation, and so on. And we've got our cultural ecosystems, which would be recreation, religious beliefs, and so on. And just because recreation is thought to be, just something you do for fun, recreation can actually still mean money for people. So in terms of tourism, if recreation is disrupted, then that can mean a lack of money for certain parts of the world. And the important thing to note is that poor communities rely most on ecosystem services directly. So when ecosystem services are compromised, then it's usually the poor who suffer the most. The more wealthy tend to have reserves built up or have the ability to buy in products and services from other parts of the world to support them when the ecosystem services fail them. Poor communities cannot do that, and they tend to suffer the most when ecosystem services are disrupted. And unfortunately, global climate change will disrupt ecosystem services. Okay. So the graphic again, drivers of climate change will impact on ecosystem functions, which will impact on ecosystem goods and services, which will in turn impact on human well-being. Okay, so I'm going to use a couple of examples to demonstrate this. First of all, looking at mangroves, and then looking at coral reefs. Okay, so mangroves. Let's talk about what ecosystem services mangroves offer to people. Mangroves give wood. Mangroves give coastal protection, water filtration, tourism, fisheries, climate regulation. So all of these different ecosystem services mangroves offer to people. So there are about 120 million people living near mangroves, which will derive some sort of benefit from these mangroves. It's estimated that mangrove ecosystem services contribute about 33 to 57,000 US dollars per hectare. And if there's over 14 million hectares, that's about 800 billion US dollars per year that mangroves contribute to the global economy. Okay, so you get the idea that mangroves provide a lot of ecosystem services, provide a lot of livelihoods for people. Now, global climate change is going to raise sea levels. With raising sea levels, mangroves will be drowned and you will lose those mangroves. So, global climate change and resulting rising of sea levels is a big threat to mangroves. Okay? Particularly on coasts where there are lots of people, because when there are coasts with lots of people and still have mangroves and people benefit from those mangroves, the mangroves cannot migrate inland with the rising sea levels, and so they are drowned. So, for instance, the Caroni Swamp is jammed up against the Solomon Hochoy Highway and the Caroni rice fields. There is really no place for the mangroves to go. At the moment, you can see some mangroves colonizing on the eastern side of the highway as they spread up drainage ditches and so on. But the mangroves on the western side really are all going to start to decline as sea levels rise. Okay? So we're going to start losing mangroves and all the ecosystem services. That means the livelihoods, the people who use the mangroves for wood, okay? Use the mangroves for fish. Use the mangroves for security, coastal protection from flooding, from hurricanes and so on. They also could use the mangroves for tourism. I mean, Nanan's Scarlet Ibis tours is a livelihood for a good number of people. Okay, maybe 50 or so people. Okay, if we don't have that tourism, then those people don't have that livelihood, don't have that recreation available. Okay, so global climate change, by eliminating these mangroves, will disrupt all those ecosystem services, which will disrupt these livelihoods of these people. Moving on now to coral reefs. Let's look first of all at the ecosystem services provided by coral reefs: tourism and recreation, food and fishing, coastal protection, and medicines. Okay, coral reefs provide about 400 billion a year to millions of people around the world. They act as nurseries for 25% of all marine life. And coral reefs are some of the most biodiverse marine ecosystems around the world. Okay, so coral reefs provide these ecosystem services, okay, which contribute to human well-being, security, provisioning, goods needed to live a good life, okay, health, and so on. So what happens with global climate change? As I've said, a warming ocean would lead to thermal stress, less oxygen, okay, sea level rise will occur because of global climate change, thermal expansion, and so on. pH levels are going to depress, and that's going to make coral skeletons more brittle and less able to be produced. Altered ocean currents are going to alter the distribution of animals, dispersing, but also nutrients. Changes in storm patterns may increase the damage to coral reefs by hurricanes and so on. So all of these factors caused by climate change will impact on the ecosystem services provided by coral reefs. Okay? And that is going to impact on human well-being. Okay? So for instance, Tobago, uses their coral reefs for tourism and recreation. If those coral reefs are constantly being bleached by thermal stress, then the tourists are not going to come. The fish are all going to die out, and food and fishing will be reduced as well. So Tobago has a lot to lose if coral reefs suffer more from global climate change, as is likely to happen. All right, coming down to the end now. So what are some of the responses to global climate change? Well, you know a lot of them. But let's class them into responses to drivers and responses to impacts. Okay? Responses to drivers tend to be harder and take longer to occur, but are more permanent and much more comprehensive. Responses to impacts, they tend to be easier and quicker, but you still haven't addressed the underlying drivers, which still need to be addressed, so the fix may not be permanent. So the responses to drivers would be controlling human population growth. Decreasing human population growth will decrease the amount of resources which are needed by people around the world, and therefore reduce the pressure on natural ecosystems. Okay? The other way that we can decrease the pressure brought by drivers is by changing the energy requirements for technologically advanced cultures or machinery, technology used by people. So instead of using fossil-based fuels, we would use fuels such as solar power, hydropower, things which do not pollute the atmosphere. Now, because carbon dioxide is persistent in the atmosphere, what we've put in the atmosphere to date is going to remain there. And it is going to remain there until forests regrow on 50% of the agricultural land and strip the atmosphere of that CO2, which isn't going to happen, at least certainly not in the near future. But we need to try and reduce the amount of carbon dioxide entering the atmosphere now. And that means reducing the amount of fossil fuels which are burnt. Those would be the responses to the drivers. So 1, reduce human population growth. And 2, change our technology to non-fossil fuels, non-polluting energy sources. If we can do that, we can drastically cut down on global climate change. In the meantime, we need some responses to impacts. So things like allowing migration of mangroves inland, trying to protect coral reefs from pollution, which would further weaken their ability to live with the changed environment due to climate change. These things need to be done to try and reduce the impacts, but we still need to take care of the drivers. Otherwise, those responses to impacts will eventually be overwhelmed because the drivers' pressures have not been released. In the long run, it's best to address both levels at the same time, drivers and impacts, to try and control the impacts on society in the short term, which would damage the world economy, and in particular damage the livelihoods of poorer people, while we formulate and respond to the drivers, okay, which are causing global climate change. Okay, well, I hope that was an entertaining lecture for you and you're still awake, and hopefully I can, yeah, okay, hopefully I will see you at the next lecture. Bye-bye.